Okay, so I think we'll probably make a start there. So thanks everyone for joining us today. I recognize, I don't recognize a lot of faces in the audience, so I think this is a kind of testament to the interest in your talk today, Ilya. So if you're a new start, if you're like a first timer to this data seminar series, basically this is part of the Live in O Center for Doctoral Training, where we have PhD students in the physics department being trained in general kind of data science techniques. And this seminar series forms part of that. So we invite speakers from a range of different fields to kind of come in and talk about their work in the context of the data science challenges that they face and also the kind of solutions and the methodology that they're working with. So we're really excited today to be joined by Professor Kuprov, who's joining us from the University of Southampton, waving in the top corner there. So Professor Kuprov got his doctorate at Magdalen College, Oxford. In 2009, he then received an EPSRC Early Career Fellowship, which he held at the Oxford Supercomputing Centre. In 2014, he was then appointed Associate Professor at the University of Southampton, later promoted to full professor, and he's still there today working as the lead of the Spin Dynamics group. And I believe today he's going to talk to us about neural networks in the context of NMR. So thanks for joining us today. Please feel free to get started whenever you're ready.
Pleasure. Thanks for the introduction. So I understand much of the audience are physicists, computer scientists, and machine learning specialists. I am a chemist, believe it or not. So I decided to treat you to a little bit of introduction as to where all of this neural network business started in chemistry and electrophysiology. So I'll show you a little bit about how a biological neuron works, and then we'll proceed to specifically the little chunk of magnetic resonance that we are doing. But more importantly, I will talk about our investigation into not just what the neural networks are doing or why they produce the answer. Those are fairly easy questions to investigate, but we managed to find out exactly how those neural networks work. And that is a much more interesting aspect of that. And so that, I think, will be the primary topic for it. But okay, so we begin at the beginning. We are all here now pretty much because of NVIDIA. As you all know, that's the world's top 500 supercomputers as a function of time. It's the total, the best one, and the one at the bottom, in gigaflop as in logarithmic scale as a function of time. We are now here at the many teraflop. And at around 2005, NVIDIA released the first double precision and single precision GPUs that are now dominating the field. And of course, the natural thing happened. So what was previously called statistics, chemometrics, systems identification, even least squares fitting comically these days is now called machine learning, sometimes with the capital letters. And the hype did not escape magnetic resonance, particularly in magnetic resonance imaging. We have these dozens and hundreds of papers about artificial intelligence resolution enhancement and feature identification and so on. And we, of course, all know how well AI resolution enhancement works. It works extremely well, as you can see. The current crop of supercomputing resources to do with machine learning is here. So world's top GPU supercomputers, of course, it's dominated by NVIDIA. But this is, let's say, the recent history of the hardware around it. And essentially, everything I'll be talking about is 30 to 40 years old as the concepts are concerned. But it only recently became so dramatically more efficient because of this computing power revolution. But let's go back into the 1940s and into the electrophysiology of the biological neuron. So that is a schematic representation of what a biological cell called a neuron looks like. You have the central body that's responsible for much of the metabolism and gene expression and so on. It's called the soma. there are little appendages here called dendrites, and one particularly long one called axon with a specialized cell called Schwann cells, which provide electrical and chemical insulation for this extended axon. And in certain organisms, this can be many centimeters and sometimes a significant fraction of a meter long. And there's about 100 billion of these things in a human brain. As you know, cell has a membrane. It's a double layer of specific molecules, so long aliphatic chain and then a polar cap at the top. It has various types of proteins that are peripheral and permeating and channel proteins. They can be glycosylated, so they're glycolipids on the outside, on either side of it. There's a mechanical strength element, cytoskeletons, with filaments of cytoskeleton, but what we want to look at specifically here are ion channels and ion pumps. If you look around a typical neuron, you will find a few interesting things to a chemist. Firstly, there's an absolute ton of potassium inside the cell, but rather little sodium. However, on the outside, in the intercellular medium, there's rather little potassium, but a lot of sodium. This is why our table salt is potassium chloride rather than sodium chloride. And if you eat a lot of sodium chloride, you probably are going to be okay. But if you eat a lot of potassium chloride, then you're going to be ill, right? So this is why table salt is sodium chloride. And the reason why that is necessary is there's a significant voltage across biological membranes. This is the Goldman equation for transmembrane potential in situation where membrane is permeable. And if you put in all of the concentrations and transport coefficients in here, you arrive at the figure of about 60 millivolts across the membrane. But remember, the membrane is just a few, a few hundred angstroms thick. It's really quite tiny. And so if you divide millivolts by, micrometers and nanometers, you get megavolts per meter. So there's a colossal electric field of about 5 megavolts per meter across the biological membranes of neurons. And why would that be necessary? Well, this is how the signaling takes place. And the way that giant voltage differential is maintained is through the ion pumps. And these are the things that actually dominate the energy consumption of our brain. Most of what we eat that ends up powering our brain is powering these ion pumps. They are ATP dependent, and this particular ion pump, it grabs 3 equivalents of sodium from the inside of the cell, binds an ATP, cleaves a phosphate of it, and inverts. It releases sodium into the extracellular medium and grabs 2 units of potassium. Note that there are 2 units versus 3 units here. There's a charge imbalance, hence the voltage that accumulates. So sodium is released, potassium comes in, and another conformational transition takes place. Phosphate is hydrolyzed off, and 2 units of potassium are released into the intracellular medium. Then there are also ion channels, and those are voltage gated. So if the transmembrane voltage drops below a certain threshold, they're open. And the ions rush in or rush out, depending on which direction the gradient is in. And as soon as voltage goes back above or below a certain threshold, they are blocked by a special plug that prevents them from functioning. So why am I telling you all of this? This is because both processes are intrinsic to how a signal is transmitted by a neuron, and then this is what the people in 1943 had used to create the first model of a perception. Okay, so we have our neuron in the resting state. And remember those minus 60 millivolts across the membrane. both sets of channels, the sodium channels and the potassium channels, are closed in that state. But if an external perturbation depolarizes the neuron somewhat, then this set of channels, the one that deal with sodium, are open. Remember, there's a lot of sodium outside and not a lot of it inside, so sodium rushes in. It depolarizes the membrane further and actually into the positive, so plus 40 millivolts. At that point, voltage-gated potassium channels open, and potassium rushes out, and the sodium channel is blocked. Because potassium rushes out in the opposite direction, it repolarizes the membrane and actually can repolarize it so far that it even overshoots. And at that point, that channel is blocked, and we are back to where we originally had been. So there's this spike that is generated first by the inward current of sodium and an outward current of potassium, precipitated by a local depolarization event. So what is going to happen, therefore, if we poke a neuron in one particular position? It will undergo this, but of course, this will trigger the same event nearby, and then the same event nearby. So there will be a traveling wave, a membrane depolarization wave, that travels in particular across the axon. And so this is how signals are transmitted in the central nervous system. They are not actually electrical currents, they are ionic currents, and they are not along the axon, they're perpendicular. These are membrane depolarization currents. And so they travel quite slowly. This is why we humans are so slow, depending on the organism. It's between 1 and 100 meters per second, so nowhere near the speed of light at which electromagnetic fields and therefore currents and conductors propagate. And then, of course, we have synapses, and these are junctions between the nervous cells, and those are chemical. So when the depolarization wave arrives here, there are voltage-gated calcium channels which open. Calcium rushes in, and it triggers the movement of synaptic vesicles that contain neurotransmitter chemicals. Those travel to the interface and burst, releasing those neurotransmitters. They bind to chemically gated ion channels, opens them up, and a depolarization wave then proceeds from there. So what do we have? So for each neuron in a biological organism, we have multiple depolarization waves arriving. But of course, depending on where it ends up, it's differently important, differently weighted. And if the total amount of depolarization here exceeds a certain threshold, then the signal is triggered and is sent down this axon. So there's a threshold here, some kind of arithmetical processing, and on it goes. So the biological neuron collects, moderates, and processes electrical depolarization waves. It then decides whether to pass the signal on and passes it on if it sees appropriate. All right. So in 1943, Warren McCulloch was staring at all of this and thinking, okay, how would I possibly model that? We've got some signals coming in, we've got some decision making here, and we have a signal coming out. As of course, everybody in the audience knows very well, this is the basic perceptron model. So there is a vector of numbers coming in corresponding to these dendrites, which collect the incoming waves. There are weight coefficients which correspond to the relative importance of these incoming signals. There's the summation corresponding to what happens on the soma. There's a bias. Different neurons are differently ready to fire, so that is necessary. And then the activation function, originally just all or nothing, like it happens in the biological system, but as you know, it has since evolved into a great number of different activation functions. And then we have the output. So mathematically speaking, of course, that's the way, right? So all the inputs, all the weights, that's a vector inner product for those of you familiar with linear algebra, and then the function. So we've got weight vector transpose times the input vector plus a scalar. And if we have a row of such neurons, then we've got multiple such neurons with multiple weight vectors, and then they make a weight matrix when you stack them vertically. And so this is an elementary step of what we today call a layer, a neural network layer. Vector goes in times a matrix plus a bias vector through a nonlinear activation function, and out it comes. And of course, this is matrix vector arithmetic. It's perfect for GPUs. But remember, this is 1943. No GPUs, no even serious computers around, right? So it had to wait until about 2010. And of course, a single GPU these days, 10 teraflops of double precision, is more powerful than the entirety of the American military had been in terms of computing power when I started my PhD project. So that was 2000, and I think that was ASCII red, 1 teraflop, 2 football fields of Pentium Pros, and now we have 10 teraflop on the desktop. So things really have changed an awful lot since then. Now, the reason why this became so successful beyond just the compute is an interesting theorem in discrete mathematics that has been proven in 1989. It's quite remarkable. For any arithmetical or logical function, and for any finite accuracy, there exists a finite network of such things that would output that function to that accuracy. So networks of these perceptrons are universal approximators. And this perhaps explains why you and I have not evolved as Turing machines biologically, but evolved as neural networks. These things are very, very flexible. And in this community, I don't need to explain to you what backpropagation training is. You all know that that's just a glorified least squares fitting with the clever implementation of the chain rule for differentiation. So goes back to Seppa-Linnemer in 1970s. And once again, the algorithm emerged then, but there were no good computers to take care of it. These days, we do it on the GPUs, and most of the thorny numerical technicalities there are saved. So this slide is something all of you are very familiar with, and so I will not stop too much here. What is important, however, is that the resulting architectures, and we are talking here about architecture in general, you will see these elements in straightforward, feed-forward neural nets. You will see them in convolutional nets. You will see bits and pieces of this in transformers, right? Even though, the flow chart of a transformer is different, at some point there's a matrix vector multiplication in there. What is important is that all of these things have this general mathematical form. A vector goes in times a matrix plus a vector through a function, times a matrix plus a vector through a function, times a matrix plus a vector through a function. Plus or minus topology and clever tricks, this is what they do. And matrix vector arithmetic is mathematically isomorphic to quite a lot of quantum mechanics, group theory, and other such things that are encountered in the modeling of the physics. We do not often have nonlinearities in quantum mechanics. Most of our operations are linear, multilinear, and so on. But ultimately, they are matrix vector operations. And in particular, a branch of quantum mechanics called magnetic resonance. All of you have encountered it in one way or another, chemists and biologists through NMR, everybody else through magnetic resonance imaging in hospital. But substantially, the act of modeling a magnetic resonance system is a giant bunch of matrix vector operations, which is why neural networks became quite common in that field as well. But once again, neural networks are 1958. So apart from greater computing power, there isn't really much new that has emerged in the last 20 years or so. Okay, so onwards to chemistry. This is something that I would have to be careful about because there's such a distribution of backgrounds in the audience. But you all hopefully remember that all elementary particles, quarks and leptons, including electrons, have this elementary property called spin. And that is the relativistic correction to angular momentum, and it's responsible for those particles having magnetic moment. Now, what is important is these magnetic moments interact with electromagnetic fields, and we can, by the application of radio frequency and microwave pulses, manipulate them geometrically. We can rotate them, we can control them, we can move magnetization from here to there, and that's the subject of the field called magnetic resonance. In particular, if we take a bunch of unpaired electrons in chemistry and biology, so free radicals, for example, we can rotate the spins of those electrons 90 degrees by applying a microwave pulse. And that's the schematic of such an experiment. So this is a microwave pulse which rotates electron magnetization 90 degrees. You know, it's originally magnetized along the magnet, and then we rotate it 90 degrees. Then if we wait a little bit, then rotate them 180 degrees and wait a little bit more, then the electrons radiate back in microwaves, and that's detectable. They radiate back a pulse that's called a spin echo. And it can be detected. There is a certain variation of this experiment which operates on electron pairs. So if two electrons are nearby, then they interact through the standard magnetic dipolar interaction. Every interaction in quantum mechanics has a frequency corresponding to its energy, and that frequency can be detected. And that's an example of just a typical oscillating pattern that comes out of those experiments. This frequency is equal to the frequency of interaction between those electrons. Of course, the frequency of electromagnetic interaction is a function of distance. And so this is a way of measuring distances between unpaired electrons in various biological systems. So, for example, you might have two magnesium ions in your chemical, for example, hydrolases often bind magnesium, but magnesium doesn't have unpaired electrons. So what chemists do is they take magnesium out and put in manganese, which is chemically not dissimilar. It can bind into the same pocket, but it has unpaired electrons, and then all of this becomes possible. So this is a distance measurement technique in biology. Sometimes you can have tyrosine radicals in certain oxidative environments. Tyrosine, which is a natural amino acid, can lose an electron, and the remaining electron is unpaired. And then they begin to interact, and distances up to 100 angstrom can be measured. For those of you who are computer scientists, an angstrom is about the length of a CH bond. So 100 angstroms you can see. And that can be done for proteins, that can be done for nucleic acids if you suitably chemically modify them. And there are hundreds and thousands of papers out there of biologists using this for distance measurement, conformational transitions, functionality of enzymes, electrochemistry, photovoltaic cells, and every system on Earth where electrons occur in a way that gives them magnetic moment, so unpaired electrons. Another example here, this is from the photosystem 1, a photosynthetic reaction system where electrons jump around when they're excited by light. There are various molecules. For example, this one contains 2 copper ions, which carry unpaired electrons, and this distance can be measured. There are, once again, various enzymes that contain, in this case, paramagnetic metal ions, and various highly engineered chemical systems in which unpaired electrons exist by design. So they're indicated by dots in chemical structures. Okay, so how do we proceed to measure those distances? Mathematics is quite straightforward if your 2 electrons are point particles. So if we assume that they're just sitting there, glued to vacuum, not doing much, just interacting electromagnetically as point particles, then this is the function that describes that oscillatory signal. It looks horrible, but it's really okay. But of course, electrons are not really point particles. They have finite extent. They're delocalized. And so the first complications that biologists have to deal with is we don't actually have a distance. We have a distance distribution, because electron is delocalized across a couple of bonds. Then chemical systems like proteins, they have a variety of geometries called conformations. And so there's conformational distribution and orientational distribution, and distribution of just about anything that, you know, a soft biological system can have. And then you have to convolve this Green's function with the distance density, so probability density of distance. Then no instrument is ever realistically perfect. Our electromagnetic pulses, microwave pulses, are not uniform across the sample, and so there are various corrections and you know, fixes that must be applied. Is a general name is modulation depths in electromagnetic spectroscopy to account. Then, of course, there are finite concentration effects. Electrons don't just occur in pairs. There are other pairs nearby at finite concentration. That creates extra artifacts, and magnetization is lost into the environment. And so there's an actual exponential decay with various vaguely physically understandable but rather hard to reproduce parameters. So we have these extra complications then. And so finally, if you put everything together, that's the distance distribution that the biologists want to know. It goes into this convolution integral and then gets distorted by modulation depths, and then gets additionally distorted by the various out-of-pair effects, and additionally distorted by the noise. And remember, we are looking at magnetic moments of elementary particles here. They are tiny. So the actual voltages that you see at the detection stage are in the nanovolts. They're at the quantum mechanical limit of electrical noise in your conductors. They're really hard to detect. And so this is what we are measuring. So this has a name. It's called the Fredholm integral equation of the second kind, but I have a much better analogy here. The task of reconstructing this distance distribution out of this measured signal is roughly equivalent to reconstructing the pig from a sausage, because you've been through this giant, you know, collection of distortions and mid grinders, including this integral, and so recovering this is seriously hard. And so, of course, the first thing that comes to mind is, why don't we use machine learning? Because this is a deconvolution problem that is mathematically close to the task of identifying a dog in an image, for instance. And the mathematical nature of the problem that we face here is quite precise and has hundreds of years of background research. We have what's called an ill-posed problem here. And a well-posed problem in the Hadamard sense, so goes originally back to Jacques Hadamard, over 100 years ago, is where a solution exists, and thankfully, in our case, it does. But the solution must be unique. And of course, in this case, because we have a convolution, that is not the case. There are many distance distributions, most of them unphysical, which are consistent with the data that we've measured. And because of that, the solution is neither continuous nor unique. And so our problem is not well posed. And not only is it not well posed, it's not well conditioned. Tiny variations in the measurement output can produce finite variations in the answer. So the derivatives of the solution with respect to inputs are not small. And problem that's neither well posed nor well conditioned is exceedingly hard to solve. A common example is inverse Laplace transform. And as you probably know, if you've dealt with these things, there's still no general solution. Okay, and that's an example from real chemistry. So this is a nanoparticle, gold nanoparticle, functionalized through the sulfur linkages with aliphatic coat. And if we put a couple of unpaired electrons using stable organic radicals here and measure distances between them, we see a peak for when the two electrons are in van der Waals contact with each other. And we also need to see, are supposed to see, this is a theoretical result, a smooth pedestal here. for all the possible distances that you can have here. And if we do the reconstruction using just this squares fitting or regularization, then this pedestal is corrupted. So it's either this peak is overbroadened or the pedestal is corrupted. And because of this ill-posedness, there is no good solution for such distance distribution reconstruction problems. And there are various band-aids, again, going back hundreds of years. One way is to say, well, okay, distance distributions in biology are always quite smooth. So why don't we look for a solution in the class of smooth functions? Well, how do we constrain a solution to a class of smooth functions? Well, we can do the standard least squares. So experiment minus simulation, difference norm squared. But we can add to it an extra contribution, which is the norm of a second derivative. And if the function is smooth, then the second derivative is small. And so that thing is small. But if the function is rough, then the second derivative is large, and so this signal increases. So this is a measure of how smooth it is, and so we can simultaneously drive down the deviation and the roughness, and this is called Tikhonov regularization after Pafnuty-Tikhonov in the 19th century. Of course, we could also fit a model. If we know that the distribution is Gaussian, we can fit a Gaussian, but we never really do. And so biologists have been frustrated by this for decades. To them, these various adjustable parameters that come about here and these obscure criteria are not really what they want to see. They want a simple push-button solution that simply reconstructs the distance distribution from the data that they have. No ifs, no buts, no computer science. And of course, that is something that neural networks are pretty good at. So we decided, well, okay, ultimately what we have is a noisy and distorted deconvolution problem of the kind that literally everybody else has in scientifically motivated machine learning, right? Object identification, signal reconstruction, deconvolution, the reconstruction problems that I've mentioned for MRI, right, where we reconstruct high-resolution image from a low-resolution one, and so on. Now, the trouble there, of course, is to train a neural network of any kind. Neural network is not a problem. Training is not a problem, right? Stochastic gradient descent is, again, decades old. The real problem in machine learning is the training database, which has to be representative, which has to be correctly annotated. And of course, most neural networks contain millions of parameters, so you need millions of carefully curated and annotated data sets. And in the history of electron spin resonance, I mean, people have recorded maybe, 20,000 spectra or thereabouts. So there is not enough training data on planet Earth, and there will never be. And this is, again, a common problem in any kind of spectroscopy that you are doing, that the only way you can generate enough training data is if you have a highly physically precise simulation package that is able to not only simulate quantum mechanically everything that goes on in your system, it needs to also simulate everything that goes on in the instrument. And not only that, it needs to simulate everything that can go right and everything that can go wrong in both the system and the instrument. So high fidelity simulations, so carefully implemented that even the spectral distribution of the noise is correctly captured. And then you can use that as the training database. Now, thankfully, as Alex already mentioned, I've spent 20 years simulating magnetic resonance systems, and we do have a simulation package with that level of fidelity. And we have to measure the spectral properties of the noise and add it artificially and so on. So we generate tens of billions of data pairs. So we start with distance distribution, and we get these two electron dipolar oscillations out. This is used for training, and then we put in the experimental data for the actual double electron-electron resonance, and it gets us the distance distribution between the radicals in our biological system. And of course, the moment we generate training data by simulation, And that was the idea that Jay Keeley, a PhD student in my group, came up with. He said, look, we're simulating it anyways. That effectively means our training database is infinite. Every time the batched stochastic gradient descent, like Adam, wants a new batch, why don't we generate it on the fly? And in that case, we don't even need to store anything. And turns out our simulator is fast enough that we can do that. And at this point, our training database is effectively infinite, and the validation problem disappears. So we can simply train until we are converged on the norm of the gradient. So we can train until the training is genuinely finished. And this is really important, as you'll see later, because we cannot afford to have any residual stochasticity in the neural network, because we want to open it up and then to analyze what it actually does. And so it's important to literally train it to convergence of the training process, rather than to a point at which some validation set stops improving. So this infinite training database came really handy. Okay, so this is the neural network that we used, you know, is from 1960s. It's a standard feed-forward vector in, vector out neural network. There are various physically motivated things in there. Substantially, the transform that we have here from this data to distance distribution is asymptotically linear, which of course is a problem if your activation functions are nonlinear. And so we had to pick up an activation function, in this case soft plus, which is simultaneously nonlinear enough at the origin for the universal approximator theorem to be applicable, but asymptotically linear enough that this thing can be a representation of a linear operation when the signal-to-noise ratio is high. So activation functions here are physically motivated and customized. The usual batch normalization, you all know what this is, fully connected layers. So this is not convolutional, not local convolutional processing. The deconvolution here is a global operation, so we do need fully connected layers, at which point we've got millions of parameters, unfortunately. And the output has the physical meaning of probability density. And so we have to have an extra renormalization layer which enforces the summation property of the probability density. So essentially a bog standard neural network, a bog standard training process with a few physically motivated tweaks. Now, I will not bore you with the biological evaluation of that the biologists did for us. We had some really surprised biologists on this, because it literally solved every problem that they have, all of the instabilities. Remember that pedestal that I was talking about? It reproduced that pedestal correctly. It started reproducing correctly multimodal distance distributions that the biologists were struggling with. And after a couple of years of to and fro between us and the application specialists, the version 2.8 of all of that took a few rounds, but essentially we arrived at a black box that the application specialists could not break. So it either produced the right answers that they were expecting to see, or it had produced an informative error message about why it cannot proceed. And that is the next stage, right? Of course, when you are doing serious biological sciences, you don't just need the answer, you need uncertainty quantification on that answer. Otherwise, this is not going to get published, right? We don't publish things on arXiv and then forget about them. We have peer review in biology, right? And that's pretty brutal. And so we need an uncertainty estimate. And the way this is done is twofold. Firstly, of course, a neural network is a continuous and differentiable function in this case. And you could backpropagate the Jacobian and then do the standard error propagation. That's one way of doing that. And we did that and implemented that. And another one is to train a number of neural networks from different initial random guesses against different databases. And then if your data does not constrain your answer at all, then different neural networks would arrive at wildly different answers. If your data constrains the answer really well, they will all arrive at the same answer. And so essentially we run the data through, for example, 32 individual independently trained networks, and we do descriptive statistics like standard deviations on their output, and that's a measure of our uncertainty. And that works, as you can see, in the case where the data constrains the answer. Well, 32 networks agree. When there's a lot of noise in there, they begin to disagree. And when the data is, seriously noisy, they disagree significantly. And when the data is completely corrupted, that's the right answer. The standard deviation here, so this red, is equal to the data. And so a neural network in this case fails gracefully. So to the biologists, it either returns the right answer or it diligently gives up and says, okay, the standard deviation on the answer is of the same order of magnitude as the answer itself, and therefore this is completely uncertain. So this is something that the biologists liked, all right? So it's a graceful fail, right? Because an honest measure of uncertainty is returned in the output. Okay, and then of course, the question that the reviewers made us address, they said, well, how do you know it's not a glorified database lookup, that it has simply learned a giant lookup table of every possible distance distribution you can have, and it's actually solving your threshold equation. And we could actually easily address that. We trained a neural network on a tri-model set of distributions, so a maximum of 3 peaks. And then we gave it an experimental data set, well, synthetically generated with noise, but a data set with 4 peaks. And it returned 4 peaks. And on any actual real-life data that the biologists got, a few hundred data sets by now, we always get the correct distance distributions. And so the next important question is, clearly this is not just an interpolator. This is not a database lookup. It can do out-of-distribution processing. Very rare to see this in machine learning. So how does the neural network actually solve an integral equation? And this is important because explainability matters, right? So there are now legal requirements in the EU and in the United States. It's called the right to explanation. Scientifically, right? Scientific reductionism, going back to Descartes, demands that we understand how everything works to the level of individual, minimal, little, small parts. And of course, that's a quote from the paper that we published on this for centuries, right? So the philosophical approach to science had been to find simple, small, fundamental laws that govern reality, and then to understand those laws and use their predictive power. But a neural network is a black box. Within this minimalist reductionist school of thought that has been dominating physics for hundreds of years, this is blasphemy. But of course, from the economical point of view, these neural networks are irresistible because you can sell them. They just work. And so we arrive here at that contradiction, and we need to understand the hell's going on inside. So these two guys, René Descartes and Karl Popper, are looking at us sort of with disapproval, and we need to understand what's going on. Okay, so what is our neural network substantially? Well, remember what I told you at the very beginning. Vector times a matrix through a function times a matrix through a function times a matrix through a function. If we give it an entire training database, that's just a giant collection of vectors, so a very long matrix in here, and that's the set of our answers. What do we mean by interpretable and explainable here? Well, we need to understand all of the intermediate signaling. We need to know what does each layer do and why. But remember, these things are fully connected. So if we permute the output of this layer and do an appropriate matching permutation of the input of this layer, it's the same network. But of course, there are n factorial permutations here. So the intermediate signaling is effectively encrypted with a one-time path for fully connected neural networks. It's completely unreadable. It's like data goes in, noise, 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 and miraculously the right answer comes out, right? And you are defined up to a factorially complex permutation. So how can we do that? Well, okay, let's think about what it would take to interpret intermediate signaling. let's assume that there exists an operator, in the simplest case, a matrix, that descrambles intermediate signaling in whatever sense, makes it comprehensible to humans, whatever that means. And we define some comprehensibility function of uncertain nature here that does that. So we want to find such an operator here, which, if inserted here, you can see this is a unit matrix, right? P minus 1. But at this point, after P, things become understandable in whatever sense. Let's think about the mathematical properties of such an object. Well, it needs to be linear here because matrix is a linear operation. It needs to be differentiable because the whole neural network is, and our interpretability probably is going to be. It needs to be invertible because information cannot be lost, and needs to be multiplicative because of our structure here. So what is it that is linear, differentiable, invertible, and multiplicative? Mathematicians call it a Lie group. And if you've been doing physics long enough, and certainly spin dynamics, in my case, you know everything about Lie groups. And so we have found ourselves rather well equipped to actually do this, because this is an object that in particle physics we understand extremely well. Okay, now the group that is common to digital signal processing, for example, Fourier transform, is called special unitary group, and over the real field, it's called the special orthogonal group. This is, for example, where discrete cosine transforms live, and Laplace transforms in a certain metric, not necessarily orthogonal in that case. And all of such operations are generated by a certain transformation called Cayley transform, parameterized by certain antisymmetric matrices. It can also be generated by exponential map, but exponentials of matrices are mathematically not very well behaved. So we took this Cayley transform. And then, okay, we thought, what does it mean to be interpretable? We think, well, okay, if we look at the intermediate signaling, and every single signal across this giant database is simultaneously smooth, then it's probably going to be understandable. We thought, okay, let's try and enforce this smoothness in the intermediate signals. Okay, a lot of mathematics later that I would not bore you with, all this matrix calculus, those of you who do machine learning understand very well and also know that it's eye-glazingly boring. We managed to formulate a minimizable functional for that, which we minimized, and thankfully its complexity is comparable to the complexity of training. And then we tried and to apply that at the intermediate linkage of those neural networks that we have trained to process this electron spin resonance data. It's the standard minimizer with LBFGS quasi-Newton, programmed in MATLAB and ported to GPU, same complexity as training, roughly. And this produces the signal that at the intermediate linkage of a deep neural network is simultaneously smooth for the entirety of the training data. And therefore, our hope is, fingers crossed, maybe physically interpretable. All right, let's take a look at the input layer. That's the weight matrix of the input layer. Of course, the usual thing, if you've ever looked at your weight matrices, it's completely incomprehensible. It's scrambled. The input dimension is ordered, of course, because that's our input signal, but the linkage dimension is completely noise-like. After we've applied the transformations that I've just talked about, oops, we have a pattern. And of course, we know that our network does some kind of signal processing. So why don't we look at the pattern in the Fourier domain? So we Fourier transform both sides, and oops, an interesting pattern emerges. Firstly, what the network does, it multiplies high positive frequencies and high negative frequencies by 0. And of course, high frequencies are noise. So what it does is bandpass denoising in this case. Look also that it takes and multiplies by 0 the 0 frequency. And the 0 frequency is a DC offset, it's the baseline. So it removes the baseline from our data by what in digital signal processing is called a notch filter. All right, so far so good. It invented a little bit of straightforward digital signal processing. But what on earth is this hourglass shape? Well, it's actually perfectly cubic. You can fit a cubic line through it. And it is cubic because in quantum mechanics, Dipole-dipole interaction depends on the cube of inter-electron distance, dipolar interaction. And so it automatically discovered that the relationship between the frequency and the distance is in this case the inverse cube. So in this giant pile of mathematics that I've already mentioned to you, this is 1 over r cubed in the dipole-dipole interaction that goes into this frequency. So it turns out our input layer has spontaneously evolved a bandpass filter against the noise, a notch filter that kills the baseline, and a frequency axis rectifier from reverse cubic to linear. And it packed it into a single layer. And of course, there's no way you can see it from just the weight matrix. You have to apply this discrumbler group transformation in order to see any of that. All right, we thought that's the input layer. Not bad, right? Some serious signal preprocessing and preconditioning. What about the output layer? Once again, the weight matrix looks like nothing much. Once you apply the discrumbler group transformation, some kind of pattern emerges that does map fast oscillations into short distances and slow oscillations into long distances. So some kind of physics in there is. But the interesting part here is the singular vectors. What this layer expects to receive and what it expects to return, right? The physical meaning of input singular vectors and the output singular vectors. Turns out that the matrix here is approximately left orthogonal, and the input vectors are oscillations of different frequencies. And so it turns out that the intermediate signaling here is frequency division multiplexed. And that's a known technique in signal engineering. It actually is called frequency division multiplexing. It's quite a common thing in television, for example. The matrix is also approximately orthogonal on the other side. And here in comes the interesting thing. If you inspect those singular vectors, they look very purposeful. There's a line, and there's a slope, and there's a wobble, and a wibble, wobble, and a wibble, wobble, wibble, and it keeps going. If you inspect further singular vectors, we thought, what on earth is this? And why is it so apparently deterministic? Well, for my sins, I'm teaching mathematics at Southampton chemistry department to chemists. And the day when we found that out, I was teaching them orthogonal polynomials, and it turns out that these are Chebyshev polynomials. And they continue up to about rank 17. So the network spontaneously invented Chebyshev polynomials, and of course, if you make them positive by applying a positive activation function, they transform into patterns of peaks. And so it turns out that neural network decided to parameterize distance peaks by Chebyshev polynomials for reasons that we still don't know, but it invented them. Anyway, so our output layer, after you descramble the signaling, using that method that I skipped the mathematical details of, it invents frequency division multiplexing at the linkage. It drops small singular values, so it's spectral filtering regularisation, so a very common regularization technique. It invents this frequency distance transform, and it invents Chebyshev polynomials. Now, if you're not shocked by now, you really should be, because a tiny neural network from 1970s has invented all by itself in 15 minutes of unattended training from a random initial guess a significant chunk of undergraduate calculus. And it is only now with the discrumbler group method that we can actually see what exactly is going on inside. And so that was enough drama to end up in PNAS, including that method. And we released the open source package that does this discrumbling in MATLAB on a GPU. We also looked at the intermediate layer, and if I do have time, do break me if I don't. The intermediate layer is even weirder here. There is, so we descrambled it, and you get this pattern. And then in Fourier domain, it's halfway diagonal, so it doesn't touch some frequencies at all. And halfway counter diagonal, it just flips the sign of that frequency. And why on earth would it do that? Now, it turns out that this basic transformation in the double electron-electron resonance spectroscopy in a certain metric is an orthogonal transformation, as all of these integral transforms are. But orthogonal group in Lie theory is not simply connected. It's got topologically connected contiguous manifolds in it, but there are discrete jumps. For example, ON, the orthogonal group in n dimensions, is actually a direct product of path-connected special orthogonal group and a discrete factor called the inversion group. But the training, the stochastic gradient descent, it's a continuous optimizer. It's a convex continuous optimizer. It cannot jump across discrete factors and manifolds. And so what appears to be happening here, and this is highly hypothetical, is that the network recognizes, or at least gets fortuitous guess, that it cannot jump across discrete factors. And so what is happening here is phase rotations. And the Lie group of phase rotations is path connected. And so essentially what's happening here is it utilizes the fact that the Cartesian product of SON special orthogonal group and the phase rotation group is a product of two path-connected manifolds. And so the resulting manifold is path-connected, and you can find an optimization trajectory through it. And then at the end, it drops back into a discrete factor in here that is the SON cron unity. This is highly hypothetical. The details are in this PNAS paper. Very mathematical. You need to know a lot of particle physics to even know this stuff exists. But it would appear that in the intermediate layers, that neural network has invented a mathematical procedure called group embedding, which is sort of postdoctoral level particle physics. So this is all, ever so slightly shocking once you start looking at it. The reviewers of the paper made us repeat all of that manually. So everything we claimed the neural network did, they told us, okay, now do it manually and demonstrate that you get the same answer. So we designed all of those digital filters in the MATLAB signal processing toolbox. We designed the transformations that I've told about with Chebyshev and so on. And indeed, we get the data in. It denoises it, it removes the baseline, it does the transformation. And so in this case, the red is the right answer and the blue is what the network returns. And we learn this method from the network. Okay, so bottom line, the ability to simulate these days, if you can simulate really, really well, can be turned into ability to interpret data without fitting. And that occurs in a lot of physical sciences scenarios. This descrambler group method that we use to understand what is going on appears to be working for digital signal processing networks, but we expect it to be working for just about any other fully connected net if you have a notion of what it means to be understandable. In our case, smoothness, but maybe something else like locality, whatever it is, it's domain specific. Same computational complexity as training. So if you can train, then you can descramble. And it answers the very difficult question of how the network works. Why the answer is produced is quite easy. There are many ways of answering that question. But how the answer is produced, that's a very, very different question and a much harder one. And as far as I know, that's the first highly generic method that answers the question of how. So open source MATLAB code, all released, commented, documented. And it turns out that the simple three-layer fully connected network in this case invented sophisticated digital filters, spectral filtering, regularization, harmonic to Chebyshev transformation. We are not so certain about topological group embedding, but it looks likely that it also invented that. And as we wrote in that paper, this is fascinating and slightly scary. So what remains is to thank a bunch of biological neural networks, one artificial neural network and one Turing machine. So the biological neural networks are Jake, Amy, Steve Forswick, Jake, Killian, Taj, Chow, Curie, PhD students in my group, are currently busy investigating the implications of all of that. MATLAB, the company, the MathWorks, have been absolutely lovely to us with a lot of technical support on parallel MATLAB and GPU. Liverfield Trust is the only organization that can possibly fund something like this, because this is such a blue skies academic research. And of course, nothing, not me, not you, not anybody present would be able to do what we currently do without NVIDIA. And this is all a part of Spinach, as a magnetic resonance simulation package, and everything I've talked about is published in this paper and released as a militantly annotated and documented open source MATLAB package. Okay, that's me, and yeah, 2 minutes overtime. Thank you for your attention.
Well, that was a really fantastic talk, taking us through from the first principles all the way through to the cutting.
Yeah, I thought I'd do a little bit of biology because none of you are biologists.
Yeah, I saw the fear in the eyes of people in the audience when you started, but I think we kind of kept with you there. So if anybody online has got any questions, please just raise your hand or drop them in the chat. And in the meantime, I'll scan the audience in person, see if we have any questions here first.
I'd really like to know more about the philosophical fallout from being able to tell what a neural network is doing, or being able to look at what it's trying to do.
Well, we are back really to empirical rationalism, right, and verifiability and understanding of things in the Cartesian reductionist sense. So we managed to reduce a black box to elementary stages here. So that's Descartes. And then, of course, testability is Karl Popper, in that you have a hypothesis, you test that hypothesis, and if it doesn't pass, that's not a good hypothesis. So the philosophical foundations of what it means to do science have not been sitting comfortably with black box machine learning. And of course, there are many other things like blame, right? If network malfunctions, who do you blame? Who do you take to court? And to some extent, I mean, this scrambler group method, it's only applicable to fully connected neural nets, and only if you have a numerical differentiable metric of what you mean by understandable. That's hard, right, to decide what it means to be understandable. And so assuming those are present, then it works. So yes, philosophy here is, we returned it to some extent within the remit of what it means to do physics.
Yep, David.
You said there were three repeats of the internals, the neural net, if I remember correctly, or maybe there were 6. It wasn't quite clear from some of your diagrams.
Mm-hmm. Or it depends. So essentially, here we do what everybody does. We just increase the number of repeats until the answer stops changing and stops improving. I think the production deer nets have six blocks. The ones that we descrambled are much simpler. They only have 2 blocks and 3 blocks respectively. Yeah.
Okay. I was just wondering, I mean, you could put your descrambler in between any of the blocks.
Correct.
Have you tried that, and do the answers change depending on which blocks you choose to put it between?
That we just did it. So Tajvar Chowdhury did this. This is in his PhD thesis that he's just about finished writing up. He discovered things that are simultaneously fascinating and disappointing. So in essence, a 2-layer network has this beautiful sophistication, right? Signal preconditioning and then processing. The middle had that cross of frequencies just jumping around. And so when Taj looked at intermediate layers of a 6-layer network, he realized that the network is procrastinating. So if you take, let's say, number 3 and number 4, the only thing layer 3 does, apparently, is it flips a few frequencies around. And then layer 4 undoes, so flips them back, and then flips a few more around, which are later undone by layer 5. plus it does something else that is sort of low-key, low residual norm, small singular values, which we couldn't understand, couldn't descramble, at least not yet. So it would seem as you add more layers, they are like the European Commission. They create work for themselves, and then they undo that work, and then they do the work again, and then undo the work until the final layer just does something physically meaningful. So they're like bureaucrats. They create work for themselves. This was our conclusion from the neural networks, which are unnecessarily deep. But then it's quite clear that we've only descrambled the principal things that it does, like maybe the first 3 or 4 singular values, the dominant singular values, and everything else is something else which we still don't understand.
Thank you.
Okay, so we have a question from the audience from Xing Na. Apologies, I've very likely mispronounced your name there. It says, thank you very much for the fascinating talk. May I ask whether you have equivalent packages in R? And could you please also share your GitHub page if you have?
So there is, it's not GitHub, it's SVN. We are old-fashioned on that, but spindynamics.org, I'll type it into the chat. Go there, go to a page that says spinach, and it has SVN code repository details and also the link to detailed documentation for all of that code. It's only in MATLAB because there's only 24 hours in a day, and MATLAB really supports NVIDIA GPUs extremely well. And it's a matrix-valued programming language which has autodiff implemented in ways. You remember, we are in the chemistry department, right? We are not sophisticated mathematicians or computer scientists. We know quantum mechanics damn well. We know particle physics damn well, but we don't know programming. And so for us, it's either MATLAB or it's not going to happen, because MATLAB, you can write poetry in MATLAB, even if you're a chemist, right? It's really, really awesome for matrix valued calculations. So sorry, it's just MATLAB, but I promise you it's extremely well documented and every line is commented in that code.
Okay, so we've got a question from Noam in the audience.
Hi, really interesting. I have a few questions. One of them is, did you try to look at, in the examples that you looked at, what happens if you apply these descrambling operators during training? So how does it actually evolve into the solutions that you end up getting?
It does, yeah. I mean, essentially, this is the tragedy of machine learning to some extent, right? So every neural network, every fully connected neural network, is defined up to an arbitrary permutation of the intermediate pins, right? So if you just take the two outputs of the preceding layer and the 2 inputs of the subsequent layer and flip them around, nothing changes, right?
Mm-hmm.
And there are n factorial such permutations. And so indeed, and this is also something that Jake and Taj have explored, you can dynamically apply descrambling during training. So you can train it a little bit and then descramble for intermediate smoothness, and then train it a little bit more. And because the transformations you apply are substantially those of equivalence, right? Because intermediate linkage is defined up to an arbitrary orthogonal transformation in the signal space. It doesn't actually even influence the figure of merit, right? So the stochastic gradient descent doesn't see these transformations.
Sure.
And this is the reason why neural networks train so easily. Imagine you have 256 intermediate pins. Then there are 256 factorial equally good global minima. And then if you have 5 layers, there are 256 factorial to the power 5 global minima on the training surface. And I think this is why it trains so well, right? Because there's so many equivalent right answers. And so yes, using this method, if you apply it judiciously at the right stages, you can train a neural network that is naturally descrambled. Yeah.
But in my question was more about the interpretability, meaning at each step, for example, of you take a step of SGD, you do this scrambling, what you would be able to see exactly what the network has so far learned,
yeah,
and
difficult
then
question.
you could see.
If you are lucky.
So that's my question. Do you actually see it after? So you could ask, for example, how many steps do you need in order to get an optimized representation that actually means something, and then stop the training instead of looking at other metrics, for example?
You are right. I mean, yes, you could, but then the question is in the philosophical concept of meaning. When you look at the signal, how do you know that it means something? Right? In our case, when I looked at those matrices, we didn't know what they were doing. And of course, after we descrambled, if we were not specialists in digital signal processing, we still wouldn't have known what they were doing. We recognized those operations visually. We guessed them. And so I would say the scrambler group transformation gives you a fighting chance of guessing what is going on, but you might still not be able to recognize the transformation you are staring at because the transformation comes from economics and physicists have never seen anything like this. Right? So it tells you that, okay, in the metrics that you have chosen to specify of what it means to you for something to be understandable, this is potentially understandable. Whether we would understand it, nobody knows.
Okay. And then another question is okay, you described everything for fully connected layers, but do you have any idea of what kind of group you would need or what kind of thoughts you need for convolutional layers, which also have symmetry properties?
But for convolutional,
and of course,
it's not even a problem. I mean, for if you've seen it in many times, in fact, for Google nets, AlexNet, and so on, because a convolutional network has a finite stride, every subsequent point only depends on a finite small number of localized preceding points. And so actually, for small convolution strides, convolutional feed-forward neural networks, they retain the data order nearly indefinitely, which is why it's easy to interpret what a convolutional neural network does, right? Remember, the first stage, I think, is edge finding, and then edge concatenation, and then object recognition. So Google and folks, when they released their networks, they already knew what they were doing. This is because convolutional neural nets, they stay ordered. And so this is not even a problem for them to begin with.
So I guess, this is, I guess, a more general point, but then any kind of symmetry group that is respected by the network, you can always map back to this kind of scrambling solution, right? So theoretically, you could always do this for any layer that has some kind of symmetry properties. So all these equivariant networks and any other kind of thing, you could know exactly what they're doing.
There will be certain technical constraints, right? You are right in that if there's any gauge group, right? So I'm borrowing terminology here from fundamental physics, right? So a gauge transformation in physics is the transformation that changes something in the formalism, but doesn't change the final answer. Right? So for example, electromagnetic gauge, phase, and quantum mechanics. So any gauge transformations of neural networks are automatically groups. But the technical question is, are they discrete groups or continuous groups? Because if they're discrete groups, like permutation symmetries, then the task of optimizing on a discrete group is exponentially hard, because you have to check every possible permutation. But the task of optimizing on continuous groups, you have a fighting chance because the underlying parameter manifolds are differential. And so you can do it with least squares or optimizations that are locally convex, like LBFGS and so on. So essentially, I would say you are right in principle. So any gauge transformation of your machine learning model can be descrambled, assuming that this transformation is continuously parameterizable.
Okay, great. Thanks. Very interesting stuff.
Yeah, I think we'll finish the questions there. So let's thank our speaker again. Yeah, that's a really amazing talk. So if, we record these talks, we put them on our YouTube channel. So if anybody wants to go this again, which I know I'm definitely going to, it'll be there, it'll be shared. So next month, we're having neural networks again, but this time in the context of astronomy. We'll be joined by Dr. Huang from the Institute of Advanced Studies, and he's going to be talking about how he calculated the dynamical masses of stars in the Hertzsprung-Russell diagram, and has got quite a good bit of good press for that recently. So hopefully see a lot of you there next month. Yeah.
Alex, could you put me on the mailing list for this seminar series? Because that sounds very interesting.
Yeah, so I'm just going to drop in the Indico page into the channel there, so you should see the chat. So if you register for that, you'll see we've got seminars up until January organized. I'm trying to get somebody from the Large Hadron Collider to deliver in February, and I'm speaking to a epidemiologist for March. So hopefully we'll have an interesting series going into 2024.
All right. Thanks for inviting me.
Thanks for coming. Really, really great. Thanks very much. Okay, bye.